Hello and welcome to 9.6, the ratio and root tests. Two really cool tests. I'm probably more a fan of the ratio test than the root test, but you can choose what you like the most. Okay, 9.17, the ratio test. Let the sum a sub n be a series with non-zero terms. Sum a sub n converges absolutely if the limit of the next term over the previous term, or I should say the next over the current term, is less than 1. If that limit's less than 1, it will converge absolutely. If, however, the limit of the next term over the current term is greater than 1, or if the limit is infinity, it will diverge. If it's equal to 1, inconclusive, try a different test. Okay. Verify the formula that 2k minus 2 factorial over 2k factorial is 1 over 2 times the quantity 2k minus 1. Okay, so we have 2k minus 2 factorial. That's going to be like saying, so 2k minus 2 factorial over 2k factorial. Now I think we've seen this before. I have kind of worked this out, so I'm hoping that this is familiar to you. That's going to be 2k minus 2 factorial over, and this would be 2k times 2k minus 1 times 2k minus 2 factorial. And this would divide out, leaving you with 1 over 2k times 2k minus 1. So this is the mistake here. It should say 1 over 2k times 2k minus 1. Now this type of skill is very important in this section. Being able to look at factorials. So this factorial, you'd go down by 1 every time. And look, they match up at some point and things cancel out. That's very important when we're doing this section, is to be comfortable with factorials. Okay. I'm going to scroll this up a little bit. So the question is here, use a ratio test, or the instruction is use the ratio test to determine convergence or divergence of the series. So we're going to do our a sub n is 3 to the n over n factorial. A sub n plus 1 would be 3 to the n plus 1 over n plus 1 factorial. So we'll do the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial over 3 to the n over n factorial. Which is the absolute value then. You could drop it if it's clear that nothing's going to go negative. Or the nice thing about that, you can get rid of negative 1 to the n if you have an alternating series. Okay, so we have the limit as n goes to infinity of 3 to the n times 3 over n plus 1 times n factorial times, we do the reciprocal here, n factorial over 3 to the n. So I expanded this term here, the n factorial. We have this 3 to the n. And we have the limit as n goes to infinity of 3 over n plus 1. And that's just going to be 0. Okay. So by the ratio test, the sum n goes from 0 to infinity of 3 to the n over n factorial converges. Let's go on to example 3. Again, using the ratio test to determine the convergence or divergence of a series. So we have the sum, n goes from 0 to infinity, of negative 1 to the n, 2 to the n, over n factorial. So our a sub n is going to be 2 to the n over n factorial, and our a sub n plus 1 is going to be 2 to the n plus 1 over n plus 1 factorial. And this negative, because of the absolute value, it's just going to go away. So we have the limit as n goes to infinity. I mean, if you want to bring the negative in there, you can. That would be negative 1 to the n plus 1, 2 to the n plus 1 over n factorial over negative 1 to the n times 2 to the n over n factorial. But by doing the absolute value, we can drop the negative in the next step. Limit as n goes to infinity of 2 to the n plus 1 over n factorial. Oh, sorry, this should be n plus 1 factorial. Times n factorial over 2 to the n. So we have the limit as n goes to infinity of 2 to the n times 2 times n factorial over n plus 1 factorial times n factorial times 2 to the n. So, sorry, this is not factorial. So I expand the n plus 1 factorial to be n plus 1 times n factorial. Now, you could, in theory, if you want to spend the time, list out n times n minus 1 times n minus 2 all the way down to 1. You have to do a dot, dot, dot in there, and same thing here for n plus 1. But the deal is n plus 1 factorial is n plus 1 times n factorial. We have a 2 to the n there. So it's going to be the limit as n goes to infinity, 2 over n plus 1, which will be 0 again. So, therefore, by the ratio test, the series converges. Okay, so feel free to pause that. I got to scroll up. Let's do it like this, and I'll scroll up again for those root tests, or the root test. Okay, so it's verified the ratio test is inconclusive for the p-series. We know this p-series will converge because the power is bigger than 1 here, right? So we have the sum as n goes from 0 to infinity of 1 over n to the 3 halves. Our a sub n would be n to the 3 halves, and a sub n plus 1 would be n plus 1 to the 3 halves. So if we did the limit as n goes to infinity at the absolute value of n plus 1 to the 3 halves over n to the 3 halves. Oh, sorry, 1 over. That's 1 over n plus 1 to the 3 halves over 1 over n to the 3 halves. This will be the limit as n goes to infinity of n to the 3 halves over n plus 1 to the 3 halves. So that's going to be the limit as n goes to infinity of n over n plus 1 to the 3 halves. Now, we could then take the limit of n over n plus 1 and raise that result to the 3 halves power. So we're doing the limit inside of this for these parentheses. And that limit's going to be 1 to the 3 halves, which is 1. So the ratio test is inconclusive for sum n goes from 0 to infinity. It should be n goes from 1 to infinity, by the way, not 0, because you'd have it undefined for the first term, n to the 3 halves. Okay, and that's it for that one. Go ahead and move this up, look at the root tests. So here's the root test. Let the sum a sub n be a series. The sum a sub n converges absolutely if nth root of the absolute value of a sub n is less than 1. Diverges if the limit of the nth root of a sub n is bigger than 1 or infinity, and it's inconclusive if it's 1, the limit of the nth root of the absolute value of a sub n. So for example 5, we get to do the root test on 2 problems. So we're going to do the limit as n goes to infinity of the nth root of 2n over n plus 1 to the n power. Now don't worry about the absolute value because this is positive. The issue you have is in case your index is even, you need an absolute value to make it positive. These are positive values. So that's going to be the limit as n goes to infinity of 2n over n plus 1. That's going to be 2. The limit there is 2. Which is bigger than 1. Therefore, this is divergent. By the root test. Okay. Last problem from this section. Okay, we have the sum n goes from 2 to infinity of negative 1 to the n over the natural log of n to the n power. So we're going to take the limit as n goes to infinity, of the nth root of the absolute value of negative 1 to the n over the natural log of n to the n power. Now, with the absolute values, I could drop this negative 1 to the n. And I'm going to do this in a couple of steps. So we have the limit as n goes to infinity of the nth root of 1 over natural log of n, that quantity to the n power. So we have the limit as n goes to infinity of 1 over natural log of n. So the limit as n goes to infinity of 1 over the natural log of n is 1 over infinity, which is 0. That's less than 1. So the sum n goes from 2 to infinity of negative 1 to the n over natural log of n to the n is convergent by the root test. And that's it. Now, in the book, page 646, there is a summary of the different tests we've had. Let me know if you have any questions. I'll see you guys online. Talk to you later.